Welcome in, everyone. So today is Thursday, July 2, 2026. And, we currently have these massive 10 trillion parameter AI models that they can pass the bar exam, right?
Oh, yeah. Pass the bar, diagnose rare diseases in seconds, all of that.
Exactly. And they write this really moving poetry. But here is the wild part, and the reason we're doing this today. If you ask two of these brilliant AI agents to just plan a simple trip across a room, they will almost certainly crash right into each other.
It's the great paradox of the modern AI era, really.
Yeah, it's like we have built systems with the vocabulary of Shakespeare, but the spatial awareness of a robotic vacuum with a broken sensor.
Right, which highlights this really profound disconnect in how we measure artificial intelligence right now. I mean, we have completely mastered generative fluency.
Their talking part.
Exactly, the talking part. But we are still fundamentally failing at structured multi-agent logic
No.
because generating a plausible-sounding sequence of words, writing a great sentence, is just not the same thing as navigating the rigid laws of physics.
And that is exactly the mission for this deep dive.
Yeah.
Today, we are taking you straight to the cutting edge of this specific hurdle.
It's a really fascinating space.
It is. So our source material for you today is this state-of-the-art paper by Mudit Rastogi from the University of Michigan. It's titled, and brace yourself, this is dense, Tensor-Coord, Algebraic Decomposition of Joint Plan Tensors for Conflict-Free Multi-Agent LLM Planning.
Quite the title, but the concepts inside are incredible.
Totally. We are going to decode the mathematics behind this paper, figure out why generative AI struggles so badly with the physical world, and explore how a 100-year-old math concept might just be the missing bridge between fluent language and, well, flawless logic.
Yeah, it's 100 years old and suddenly relevant again.
Right. So, okay, let's unpack this. Why are large language models crashing and burning when it comes to simple multi-agent coordination? Like, what is fundamentally broken here?
Well, to understand the failure, you really have to look at the fundamental architecture of these models. I mean, large language models are optimized for one primary task, and that is next token prediction.
You just guess the next word.
Exactly. They analyze the text that came before, and they probabilistically guess what the next word or, token should be. They are inherently not built for principled state space search.
State space search meaning?
Meaning explicit tracking of an environment, satisfying hard physical constraints, and systematically exploring a massive branching tree of possible actions without losing the thread.
Got it. So it sounds like the difference between talking about playing a game of chess and actually playing it. A language model knows what a chess move sounds like in a sentence, but it doesn't actually have a mental picture of where all the pieces are on the board.
That is a very accurate way to frame it, yeah. The model approximates planning by retrieving patterns it's seen in its training data, rather than genuinely reasoning through a physical state space.
Oh.
And the paper highlights this with some pretty stark statistics. On standard planning benchmarks, a model like GPT-4 achieves only a 12.3% executability rate.
Wait, 12.3%? That's terrible.
Right. It's incredibly low. Furthermore, even now in 2026, hallucination rates remain a huge roadblock. The text notes that hallucinations occur at a rate of about 1.2% at 32,000 tokens.
Which doesn't sound too bad.
Until you stretch the context window. It climbs to 3.2% when you push it to 128,000 tokens. And a core philosophical point in Rastogi's research is that these hallucinations, they aren't a traditional software bug.
You can't just patch it out.
Exactly. You can't just issue an update to fix them. They are deeply, deeply rooted in the probabilistic nature of the LLMs themselves.
Okay, wait, I have to push back on this a little bit.
Yeah.
Because, we're tracking a lot of new developments, and the tech giants just released all these mega models meant to fix exactly this kind of logical reasoning.
Sure, they have.
I mean, Meta just dropped MuseSpark back in April with that massive contemplating mode, right? Running multiple agents in parallel.
Yeah, that was a big release.
And OpenAI has GPT 5.4 Cyber, and Anthropic's Claude is quite literally dreaming between sessions to self-improve and delegate tasks. So if you put these brilliant models into conversational frameworks like AutoGen or Crew AI, shouldn't they just be able to talk it out?
Talk it out. How exactly?
Like one agent says, hey, I'm walking through this grid square, and the other says, okay, cool, I'll go around.
It seems like a logical assumption, right? Especially given how well they converse with us in natural language. But the mathematics of multi-agent planning completely dismantle that conversational approach.
Really?
Yeah. When agents just try to talk it out, they fall victim to what's called a combinatorial explosion.
Okay, I picture it like this. It's like asking 5 brilliant but deaf and blind chefs to cook a complex meal in one tiny kitchen without a head chef.
That's a great image.
Like, they know their individual recipes perfectly, but because they can't coordinate the shared physical space, they're just going to bump into each other and drop the food all over the floor.
That analogy holds up perfectly under the math. In the paper, Rastogi actually breaks down why current conversational coordination methods fail so badly.
Oh, how so?
Well, if you try sequential planning, which is having Chef 1 plan their route and then asking Chef 2 to plan around Chef 1, you introduce a massive ordering bias.
Because Chef 1 goes first.
Exactly. Chef 2 has to accommodate Chef 1, but Chef 1 never had to accommodate Chef 2. It completely fails to resolve circular dependencies where two agents need to, mutually adjust their paths.
Right, because Agent 1 already finalized its plan and stopped paying attention. It's totally rigid.
Precisely. So to fix that, you might think, well, let's use a single LLM and just prompt it to plan for everyone simultaneously.
Which is joint prompting, right?
Yes, joint prompting. But the joint action space grows exponentially, and this is where the context window just shatters. The text provides this really sobering mathematical reality. If you have just 3 robots taking 20 steps, with 7 possible actions they can choose from at each step, the number of possible joint plans is 10 to the 50th power.
10 to the 50th. I mean, that is an incomprehensible number.
It really is.
It is vastly more than the number of stars in the observable universe just to figure out how 3 little robots should take 20 steps across a room.
Exactly. And you simply cannot fit that mathematical reality into a natural language prompt. A language model will just drown in the possibilities and start hallucinating safe-sounding but physically impossible routes.
Wow.
Which really raises an important question. If natural language and conversational frameworks cannot coordinate these agents, what can?
Which brings us directly to the novel solution presented in the paper. Because natural language completely fails at spatial coordination, we have to translate these plans into a strict mathematical space. And the tool Rastogi uses to do this is a tensor. Now, for you listening, if you are dealing with standard two-dimensional data, you would just use a matrix. Think of like a standard spreadsheet with rows and columns.
Just a flat page of data.
Right. But here we have multiple overlapping variables. So we need a 3D data structure. So imagine a 3-dimensional cube of sticky notes. That is a tensor.
That's a really good way to visualize it.
So in this paper, the system takes the messy language output from the AI and basically locks it into this 3D tensor where the 3 dimensions are the agents, the time steps, and the actions.
It is a highly effective way to encode the physical environment. But, the true genius of Tensor-Coord isn't just dropping data into a tensor. It's the use of what the researchers call a soft tensor.
The soft tensor trick is fascinating because it addresses how AI actually thinks, right?
Yeah, exactly. So if a robot's language plan says it wants to move north, you might assume we just put a 1 in the move north coordinate of our mathematical cube and a 0 in all the other action coordinates.
Like a strict binary.
Right. That would create a hard binary tensor. But in linear algebra, if you have a massive tensor filled mostly with zeros, it's considered sparse.
Okay, sparse data.
And when an algorithm tries to decompose or analyze a highly sparse tensor, it often encounters mathematical instability. It essentially hits a wall where the math just breaks down and degenerates.
It crashes.
Yeah. So Tensor-Coord uses probabilities instead of binary numbers.
And this is where the paper mentions assigning a gamma value of 0.8.
Right, exactly. Yeah. Gamma simply represents the confidence weight assigned to the chosen action. So if the LLM chooses move north, the system assigns a 0.8 probability to that specific action in the tensor.
What happens to the rest of the probability?
The remaining 0.2 is then evenly distributed across the other 6 possible actions the robot could have taken. So every other action gets roughly a 0.033 value.
Oh, I see. So you never have a true 0 in the math.
Exactly. By ensuring every cell has at least a fractional value, the system performs what is called a full rank relaxation.
Full rank relaxation.
Right. It keeps the algebraic structure stable and solvable, preventing the algorithm from crashing, while that heavy 0.8 weight still clearly dictates the robot's intended path.
Here is the critical piece for you listening. Large language models are inherently probabilistic, right? They don't operate in absolute ones and zeros. They operate in likelihoods.
Exactly.
So by converting the LLM's plan into this probabilistic soft tensor, the researchers are actually translating the physical environment into a mathematical language that perfectly mirrors the AI's own neural architecture.
That's the beauty of it.
Think of it like being a manager dealing with highly creative, somewhat chaotic employees.
Yeah.
Like to organize their week, You don't use abstract poetry to talk to them. You put their schedules into a rigid grid.
Right, a calendar.
But because you know how they operate, you don't say you have a 0% chance of being anywhere else. You say, I am 80% sure you will be at this meeting, and there's a 3.3% chance you might wander off to the break room.
That is a brilliant analogy.
You've built a mathematical schedule that accommodates their nature while still keeping them on track.
And once we have constructed this probabilistic cube, we can finally apply the mathematics required to find the physical collisions.
Okay, how does it find them?
We achieve this through a technique dating back to 1927 called Canonical Polyadic, or CP decomposition.
1927.
Yeah, almost 100 years old. The goal of CP decomposition is to factorize our complex tensor into a sum of independent rank 1 components. You can basically visualize these components as the fundamental threads of behavior running through the agents, the time steps, and the actions.
So we are essentially pulling the individual threads out of this big tangle to see what is actually going on.
Exactly. And this leads to the coordination complexity metric in the paper, which they define as CC equals R star minus N divided by N.
Okay, let's break that formula down.
So if N is the number of agents, say 3 robots, and R star is the minimal number of threads the math had to pull out to represent the whole system, then if R star equals N, every robot has exactly one perfectly independent thread.
So that is the ideal state, right?
That is the ideal state. If R star equals N, the mathematical model confirms that the plans are completely independent. There are 0 interagent dependencies, meaning there are no physical conflicts. The plans are completely clean.
But if R star is greater than N,
then it proves the independent model wasn't enough to capture the behavior.
right, there is a tangled web. The excess threads, the amount by which R star exceeds our number of robots, is a direct computable measure of how tangled the robot's plans actually are.
Yes.
It objectively proves that coordination is required. But, and here's the catch, knowing there is a tangle doesn't actually tell us where the knot is.
Exactly.
Which is where the paper introduces the concept of the residual tensor.
Right. So when you subtract the perfectly independent model, the ideal state where R star equals N from the actual messy soft tensor we just built from the AI's plans, you are left with a remainder.
Like in basic division.
Exactly. And that remainder is the residual tensor. It isolates all the behavior in the joint plan that literally cannot be explained by the agents acting independently.
It makes me think of noise-canceling headphones. Like the processor inside your headphones listens to the constant background hum of an airplane cabin, calculates that predictable independent baseline frequency, and then inverts and subtracts it from what you're hearing.
That's a great way to think about it.
And the residual sound that makes it through to your ear is the sudden, unpredictable spike, like the person next to you dropping their tray table.
Right, the anomaly.
So if you subtract the predictable baseline math of the robots moving independently, the residual spike in the tensor is the exact mathematical location of 2 robots crashing into each other. You don't even need to write a domain-specific rule that says robot 1 cannot share grid square C4 with robot 2. The math just inherently highlights the anomaly.
It does. The residual mathematically isolates the exact coordinate of the crash, the specific agent, the time step, and the action. However, this creates a totally new bottleneck in the process.
Oh, why is that?
Well, we have found the exact coordinates of the conflict in a mathematical space, right? But large language models cannot read algebraic tensor residuals. They only process natural language.
Oh, right. Because if I hand an LLM a raw tensor residual, it's just going to hallucinate a response. It doesn't natively speak calculus.
Exactly. We have to turn this 100-year-old multilinear algebra back into English instructions that the AI can actually act upon.
Okay, so how do they bridge that gap?
To bridge that gap, the Tensor-Coord framework utilizes a second mathematical process called Tucker decomposition.
Tucker decomposition, okay.
Yeah. If CP decomposition is the spotlight that tells us where the crash is, Tucker decomposition is the prism that separates that crash into its component parts to tell us why it is happening and who is involved.
Okay, so it breaks it down further.
Right. It takes the tensor data and calculates the covariance between the different dimensions, grouping them into 3 specific interpretable factor matrices. We call them matrix U, matrix V, and matrix W.
Okay, let's explore how it actually extracts that information, because this is really where the bridge from math to language is built, right?
Yes. So, matrix U represents agent roles. The algorithm scans the tensor looking for statistical correlations in spatial behavior.
Like what?
For instance, it might see that Robot 1 and Robot 3 both have really high probabilities of occupying the exact same quadrant across several overlapping time steps. Because their data heavily correlates, the math objectively clusters them into a shared role.
Oh, I see.
It objectively identifies that these two specific agents are tethered together for this portion of the plan.
So it finds the hidden structure without us telling it what to look for at all. And matrix V, does this do the same thing for temporal phases?
Yes, exactly. Matrix V groups contiguous time steps into distinct phases of the plan based on activity levels. It might identify time steps 1 through 4 as an initial movement phase, time step 5 as a high-density crossing phase, and the remaining steps as, say, a delivery phase.
Okay, the matrix W.
Finally, matrix W represents action types. It clusters functionally similar actions, like grouping all horizontal avoidance movements together.
And this completes the loop. So the system takes these matrices, the clustered roles, the specific phases, and the action types, along with the exact coordinate of the crash, and it automatically translates that mathematical data into targeted natural language constraints.
Right back into English.
So instead of giving the AI a generic, totally unhelpful prompt like, hey, don't crash into Robot 2, it gives it a highly specific, mathematically backed instruction. It literally generates a prompt that says something like, avoid position 2 go 2 at time step 5, Robot 2 will be there. Synchronize at phase boundary 5.
It fundamentally changes how we interact with the language model. We are no longer asking the LLM to blindly search a massive state space.
Right.
We're using algebra to calculate tight, deterministic boundaries, and then asking the LLM to use its natural language fluency to generate a path strictly within those specific boundaries.
So for you listening, picture this as the ultimate AI feedback loop. The AI uses its creative fluency to generate a messy, probabilistic plan. The system drops that plan into a 3D tensor cube.
The math takes over.
The CP decomposition math finds the exact tangled threads. The Tucker decomposition math extracts the specific roles and phases. The system translates that back into strict boundaries in plain English. And then the AI tries again, but this time with rigid guardrails.
It's an elegant loop.
It is. But, theory is one thing. The paper actually details how this holds up when tested in a simulated environment, which is where it gets really interesting.
Right. The researchers simulated this using a grid world environment, which essentially functions like a warehouse floor where robots have to navigate to deliver packages. And they used Azure OpenAI GPT-5 as the backend model to generate the plan.
And the results from that GPT-5 simulation are pretty revealing about the limits of this approach, honestly.
It are.
When they ran the easy configuration, which was just 2 agents on a 5x5 grid, the system hit a 100% success rate. It converged on a totally conflict-free plan in an average of just 1.4 iterations.
Super fast.
Yeah. And on the medium setting with 3 agents, it held strong with an 80% success rate. But when they pushed it to very hard, which is 5 agents on a slightly larger 6x6 grid, the success rate plummeted to just 20%.
Which is a huge drop-off. But if we connect this drop-off to the bigger picture, the root cause is a phenomenon known as the constraint interaction problem.
Okay, how does that work?
Well, when you have 5 agents operating on a confined 6x6 grid, the environment is incredibly dense. So when the tensor math detects a conflict between Robot 1 and Robot 2, it issues an English constraint to fix it.
Right, avoid this square.
Exactly. Robot 1 dutifully alters its path to comply. But because the grid is so congested, that new avoidance path immediately pushes Robot 1 directly into the path of Robot 4.
Oh, it causes a cascading traffic jam. You fix the collision at one intersection, and the rerouted traffic just backs up into the very next one.
Exactly. The available physical space for avoidance shrinks dramatically as the number of agents grows, while the number of potential conflict zones grows exponentially. The iterative loop simply starts playing whack-a-mole with collisions.
That sounds incredibly frustrating for the system.
It is. However, within this failure mode on the hardest difficulty, the researchers documented a truly fascinating emergent behavior.
Yes, the fallback paradox. This was incredibly surprising to read. What actually happens to the language model when it hits this wall?
In these dense, highly constrained scenarios, the system is generating a massive amount of rules to avoid those cascading collisions. The researchers found that when the LLM is fed too many constraints, specifically they noted more than 15 constraints per agent, the model experiences a form of cognitive overload.
It just shorts out.
It simply cannot process a viable path that satisfies all these conflicting rules. So it gives up on complex navigation and falls back to the simplest possible safe action. It issues wait commands.
The AI just gets overwhelmed by the traffic, throws its hands up, and decides to park and wait it out.
Yes.
But the paradox, and I think the real discovery here, is that by giving up and waiting, the AI accidentally solves the underlying mathematical problem.
It really does, because a stationary robot cannot collide with a moving robot.
Right.
This strategic weighting drastically reduces the tensor residual complexity we discussed earlier. It clears the traffic jam. It highlights that explicit weight-based coordination, simply pausing, might actually be one of the most efficient ways to resolve high-density multi-agent conflicts.
So the LM failed this complex navigation task, but in doing so, stumbled upon a highly effective coordination strategy just by sitting still. Wow. So what does this all mean? We started this deep dive wondering why the most advanced generative AI in the world struggles to walk across a room.
Yeah.
And what we learned is that the secret to making these incredibly fluent models reliable in the physical world isn't necessarily pumping them full of more parameters.
Right, bigger isn't always better here.
And it isn't writing clever natural language prompts. It's taking their probabilistic outputs and wrapping them in rigid, 100-year-old multilinear algebra. We literally have to force mathematical logic upon them to constrain their chaos.
It is a really clear demonstration that language alone is insufficient for physical coordination. You need the geometry of tensors to accurately map the reality of space and time.
So for you listening, the next time you scroll your feed and see a headline about a massive new 10 trillion parameter model, you will know the secret limitation that tech companies are actually fighting behind closed doors. You will know that underneath the hood, words aren't enough, and they are relying on three-dimensional mathematical cubes to keep the robots from crashing into the walls.
And, looking at this research, it leaves us with a rather provocative final thought.
Oh.
Yeah. If an advanced artificial intelligence requires a higher dimensional algebraic tensor to coordinate just 3 agents on a tiny 5x5 grid without crashing,
Yeah.
what does that say about human society?
Oh, that's interesting.
Right. Our human cultural norms, our traffic lights, our cues, our unwritten rules of politeness, are these just our brain's biological version of Tensor-Coord constraints?
Yeah.
Are we simply using culture to compress the infinite exponential complexity of human interaction into a manageable, conflict-free space?
Politeness is a biological tensor constraint to reduce our joint action space. That is a brilliant thought to end on. Definitely something for you to mull over the next time you're stuck in traffic or, waiting in line for a coffee. Thank you so much for taking the plunge with us into this deep dive today. Stay curious, and we'll catch you on the next one.